Good afternoon, good evening, and good morning, wherever you are. Thank you for joining us at the second episode in the series of webinars with Professor Guy Andrebois. Today, we have a pleasure of running the second seminar after bit, and we'll build up on the first webinar, which was about the evolution of automation. Today, Guy will talk us through the human elements in large complex systems, the role of people in interconnected systems. Very briefly, for those who do not know Guy, Guy is a professor at Centre Supélec in Paris-Saclay. He had different positions, chairs, boards, and so on. So he has worked in NASA Kennedy Center, in NASA Ames Research Center. He's been in different positions, and he's, amongst anything else, it's a cognitive engineer. So for today, second webinar, and towards the end, I'll announce the third and the fourth with him. A bit of logistics for today. For the audio settings, you are inhibited the microphone and videos, but you manage your own audio. If you heard the music, that means you can hear us. If you have any questions, please put them in the Q&A. For any salutations, suggestions, other experiences, use the chat. The recording is only for quality control, and we will not dispatch the recordings. So without further ado, on behalf of myself and my colleague and friend Jörg Leonard, who are the sponsors of those webinars, I would like to pass the floor to Guy, and let us roll. Guy, the floor is yours.
Thank you very much. Can you hear me? Okay. So I'm going to put the slides.
Loud and clear. We hear you well.
Okay. Okay, so good afternoon. Thank you very much for attending this second webinar. Today, I'd like to talk about large complex systems and the role of people in these interconnected systems. So what I'm going to say is based on my experience, both in academia and industry and government. I worked at UNERA, I worked at NASA with Airbus, and mainly with aeronautics and astronautics. And recently, I'm the director of a chair at Central Supélec and SCI Institute of Technology. And we work with other fields, oil and gas, medical, and rail as well. So in fact, what I'm going to say is applicable to a wide variety of complex systems. I would talk about socio-technical complex systems. So first, I'm going to introduce what a complex system is about for me. Then I'm going to emphasize the meaning of what is a system and what do we mean by system. And then I like to raise the distinction between task and activity, what we are planning to do and what we really do. And I like to show also the evolution of human factors and ergonomics, and to what we're doing today in large complex systems. And I like to define this new discipline that we call human systems integration, HSI. And then I'm going to introduce a method that we are developing right now called PRODEC. That is an operation-centered design method and tools towards HSI. So can you see my full screen? Because I don't see everything myself.
Yes, Guy, we are seeing well. You are in full screen presentation and we hear you well.
Okay, good. So last time I talked about automated systems. Today I like to talk automation, but more than that, about automating large complex systems. and probably providing the start of a roadmap for that. I've been working on complex system in aeronautics, as I said, in space, and I'm going to use some examples. I will not enter into details here on this slide. During my career, about more than 40 years now, I've been working on cockpits and in aeronautics, but also in space. I worked on the shuttle cockpit as well. And I worked on space systems such as the Lunar Electric Rover, that is called now SEV, and also the redesign of the firing room at Kennedy Space Center in Florida. But I worked on other things, but I wanted to introduce this to say that we started by trying to improve the interaction with these systems by corrective ergonomics methods and tools, and improve the user interface. And I'm considering that the user interface is a concept of the 20th century. And I will tell you more about what we mean by human systems integration in the 21st century. So in fact, we move to correction, to interaction, to integration today, and other things that I will tell you in a few minutes. So first, we should talk about human-centered design. I wrote a book in 2013. The book the title is Orchestrating Human-Centered Design. And in this book, I asked the question, HCD for whom? Well, it's for the people who are going to use these systems or are going to be involved in this system. And the more we go, the more we see that we jump from interaction of a human with a machine to the inclusion of people in large social cognitive or social technical systems. So, and in fact, engineers, designers, developers, manufacturers, certifiers are included in this approach to human-centered design. So HCD assumes that there is always the human element everywhere, from the beginning of the life cycle of a system to the end of this system, when the system retires. So the question is, how do we consider the human element? There are various kinds of approaches, and I will provide you with one. What are the theoretical and practical methods and tools? I will provide some, at least one product in the end of my talk. HCD of social technical systems need to be thought in our digital world. More and more, we deal with software and computers everywhere. There is a software almost everywhere. And this software now is interconnected with other software. So we need to consider the triptych that I call the top model: technology, organization, and people. All together, when you design a new technology, that will modify the way you organize in a company or in a society, and the competence of people will change. So in fact, we need to deal with change management there. And also we need to think in terms of life cycle of systems. A system has a birth, a life, and death in the end. So in fact, we need to deal with that. So, I'm involved within INCOSI, International Council on Systems Engineering. And for the last 3 years now, we developed the concept of, and discipline called human system integration. And we we have produced a chapter for the future systems engineering handbook of INCOSY, and this chapter will be called, of course, human systems integration. And we try to better understand what disciplines, basic disciplines are involved in human systems integration. The first one is systems engineering that deals with socio-technical systems, system of systems, agile development, design and system thinking, and also model-based systems engineering, MBSE. But it deals also with human factors and ergonomics. That means, for short, task and activity analysis, human and organizational performance evaluation and metrics, and other things. And the third discipline is information technology that deals with human-computer interaction, artificial intelligence, visualization, modeling, and simulation. We cannot do without modeling and simulation today. And I will come back on that. And then it's like the three musketeers. There is a fourth one that is actually the operational domain. For instance, you cannot do exactly the same in medicine and in aerospace or in nuclear. So the competence in the operational domain is really crucial. That provides operational expertise and experience that we need to deal with experts, especially for eliciting scenarios. I'm going to come back on that. PRODECT is a scenario-based design method. And experimental test personnel, we need to run human-in-the-loop simulation as early as possible to figure out the human factors involved in the new design. Then there is another layer that we try to anticipate. We call that the perspective. A perspective, and this is a non-exhaustive list, but we are writing right now a primer on HSI at INCOSY. This will be a primer with 4 volumes, around 100 pages. And we going into more details on safety, competence and professionalism, sustainability, habitability, usability, UX, occupational health, social, cultural, and operational organizational factors, training, HSI planning, human factors engineering, workforce planning, and integrated logistics, which is actually related to support and maintenance. So we need to deal with this all perspectives at each step during the life cycle of a system. And at the center, we have 3 things that come back all the time: people, organization, and technology, or technology, organization, and people, TOP, top model, within an environment that we need to make sense of it. So all this leads to this new discipline called HSI, Human Systems Integration. And I will try to describe that in more detail. So last time I presented this slide, but in a different way. Now I want to introduce, this new discipline HSI. When we automated during the 20th century machines, we started by developing autopilots, for instance. As early as the 1930s, we had autopilots on commercial airplanes. Boeing developed one in 1932. This was a cognitive function transfer from human skills of humans into the machine using electrical engineering, mechanical engineering, and control theory. So in other words, at the first level of interaction, we have sensory motoric functions that people use, and we transfer this function into the machine. We call that the skill-based behavior. This Jens Rasmussen defined that a long time ago in 1983. And then if you cannot succeed by using this first subconscious level, then you have to go to a conscious level where you need to apply rules. You need to think, and you need to pattern match the situation with a pattern that you have learned before, and that leads to the execution of tasks. So it's called the rule-based behavior. And we went, we moved to this level in the 1980s. If the first level is the autopilot on an aircraft, this is the level of the flight management system. It's on top, and it's more, related to, in engineering, to operations research, optimization, expert systems, these kind of things. Then, if you don't succeed with that because you don't have these rules in your long-term memory, then you have to go to another level that is called knowledge-based behavior, where you need to identify the situation. You need to make sense of the situation that you observe. It's not already stored in your memory. You have to make sense of it. You have to give a meaning, to make sense of it. And then you have to make a decision based on the goals that you have. And then you need to make a plan, to find what are the tasks that you need to execute. At this level, we developed a discipline called cognitive engineering during the 80s, 90s, and 2000. And human and social sciences were at stake there. So all this, we can say circa 2000. That's a bit before, but this is okay. Then we jumped from basic automation to supervisory control, and then to human machine teaming. And then what we call autonomy today is at this level. And then I want to emphasize this autonomy issue, in fact. And then I want to show you that we cannot be autonomous if we don't consider the environment where the agent is. And this is really important to make sense of all this. So today, artificial intelligence pretend that we could model and make some machines that could handle this level. It's going to be extremely difficult to do it without human intervention or human activity. The problem with humans is, the good thing is humans can be creative. Creativity is really one of the main assets of people, which is very difficult to create in a machine. On the other hand, people can make mistakes, human errors, and then this is why we want to automate. But in fact, at some point, I mean, the human will always be there. So this is my hypothesis, my assumption. So if you want to read more on this, we recently, had a paper accepted. I mean, it's not 2022 to appear; it's 2022. Now this article will be in the work journal, an international journal. The machine as a partner. The idea is at this point, machines could be partners instead of tools. So we will come back on that. So in fact, in this evolution, it's important to make a distinction between task and activity. This is coming from human factors and ergonomics, HFE, human factors and ergonomics. For a long time, we have done corrective ergonomics, as I said before. We were building a system, and then afterwards using it and trying to, to adapt the people to the machine. So what the human factors and ergonomics experts have done is that they observe the activity. Think about the flight test testing a new aircraft, and you observe the activity of the pilots and other personnel. The problem is when you can observe the activity is when the the overall system is built, it's often too late to make deeper modification. So this is why, I call that the syndrome of the user interface. We have developed user interface to compensate some issues in the design of systems. And this was extremely difficult to take into account, to consider activity in the first place, at design time, if you want. So in fact, we have done that for a long time. In other words, I mean, I want to come back on that. The task is what you need to do, the prescribed task, and the activity is what we really do, what the effective activity that you produce. So in fact, the activity could be tested only when the overall system was built for a long time. Then came computers, circa 1980s. And then we started to see a new discipline coming, human-computer interaction, related to computer science. And, and then this new discipline called interaction design. We were starting to design the way people interact with machines that were highly digital. And so in fact, at that time, task and activity were very close, in fact. And then we developed task models, task analysis methods, and we could use that at design time, but on very simple systems, when you deal with a large complex system, this is another story. And then came the 2000, and then we started to see that the digital era was there, and we could run virtual prototypes very early. If I take, for instance, the Dassault Falcon 7X, I mean, it was fully designed as a gigantic piece of software that could be flown virtually as a video game, if you like, a very sophisticated video game. And then you could test at design time the activity. You didn't need to wait that the full aircraft was fully built to check, how the people will deal with the system. And then, you could test the activity at design time, which makes a big, big difference. The problem is, and I wrote a book on this, human system integration from virtual to tangible. One of the main concept that emerged there is the concept of tangibility. Is the virtual prototype tangible enough to make decisions? And the tangibility could be the distance to the real world, of a system. And then I will come back on the issue of flexibility in a few minutes. So in fact, you see the evolution today. We move from human facts and ergonomy, HFE, to human-computer interaction, HCI, and today to human system integration, where we can integrate human and machines at design time in a much easier manner than before. At the tangibility issue, if we can master the tangibility issue enough. So something, this evolution is the evolution from mechanical engineering in the, before the 1980s, where we developed industrial engineering, physics and mathematics, mechanical engineering, and HFE was there to compensate. Then we moved to HCI with, I call that artificial intelligence 1, which is the first 1980s artificial intelligence developments, computer graphics, software engineering. And then we moved to HSI with systems engineering, artificial intelligence 2, I mean, what we see today, complexity science, organization, design, and management. I will come back on organization because this is becoming the real issue today. And modeling and simulation, that is actually a real support to HSI. then all this is moving along with an increase of complexity of systems. Complexity is related to, the connectivity, the interconnectivity of systems. When you touch somewhere, then there is a propagation of issues in all kinds of directions you cannot anticipate sometimes. So in fact, we need to master that. So we moved, and something else I want to say is, human systems integration is getting very close to artificial intelligence in the multi-agent sense, not necessarily in the neural networks or machine learning or things like this, but in the multi-agent sense. And I will come back on that. So in fact, we moved from physical to cognitive and to social today, introducing this issue of autonomy and flexibility. So in other words, today we have this issue of making more and more autonomous or semi-autonomous systems, including people. Making people autonomous, if you have a handicapped person, you provide with a technology that makes this person more autonomous. I mean, this is, we should look not only on the autonomy of machines, but also the autonomy of people. I'm not saying that we are working only for handicapped people, but as far as I'm concerned, I always said that flying is not a natural thing for people. We are handicapped compared to birds. So in fact, we use this prosthesis of an airplane to fly. So in other words, this issue of autonomy is becoming more and more important today as a social issue. In other words, the more agents become autonomous, the more coordination rules you need. It's like road rules. We are autonomous in our car, but if we don't have road rules, we're going to have accidents. So I wanted to draw this evolution here and say that complexity needs not, we should make a difference between complex and complicated. Complicated is not necessarily good. We make systems that can be complicated. We can simplify them by being more rational and useful. Complexity is another story. When you have a complex system, it's complex. The human being is complex, and you cannot decompose the human being as you want, to learn or to better understand parts. For instance, the concept of separability is a big issue here. You can separate the hand of a human and replace it by another hand. You need a very, very good surgeon for doing this, but that's not possible for the brain. If you remove the brain from a body, then you kill the whole system. So in other words, you need to become more familiar to complexity, and the more familiar you are with the complexity, and the more you understand the system. So in other words, the opposite of complexity is not necessarily only simplicity, but familiarity, in fact. And this is very important to understand, because we are entering into this complex world in the sense that people are more and more interconnected, and we need to better understand what is going on there. Okay. So we need to deal with this complexity. So let's imagine that we want to go to Mars or to the moon, okay? This is a complex issue, okay? And then you build a spacecraft, and then you need to build a ground system, and then what you usually do is that you start to see how these three systems, and there are more systems like that, but these three systems interact among each other. Then you start to build, a set of functions that are interconnected among these systems. So in fact, what you built here is what we call today a system of systems. So the system of systems is a recursive definition of a system, in fact. And then you need to deal with this separability. What can you study in isolation from the rest, and what you cannot study in isolation from the rest? You need to, you need to better understand this, because otherwise, I mean, you will end up with something that is not correct. So if I generalize this, a complex system is a living organism. Separability is an issue. What can you separate and study in isolation? Second, the complexity is not only in the nodes of this complex system, but is in the mostly in the connections. If you take into, if you look at the brain, for instance, you have millions of billions of interconnections. When the brain works, then these interconnections are used to to enable the neurons to interact among each other and creates something else that we called, these yellow functions here, that we call emergent functions. Consciousness is an emergent function. It's not in the nodes, it's not in the neurons, it's not in the connection, but it's emerging from the activity of the complex system. And then, when you build a new, let's assume you build a new air traffic management system, then something that you have to look for is these emergent functions. And then the more you know about these emergent functions, the more you see a system that is becoming mature. Maturity is about discovering, not only that, but this is important, discovering these emergent functions. Sorry, there's a typo here, emergent without S. This is my French coming back. Okay, so that's important. And I will come back on maturity later. So what are the properties of a complex system? Well, first, large number of components and interconnections among them. Second, many people involved in its life cycle. When you build a complex system, there are many people. From the beginning of the birth of the system, the first idea and design, to the the retirement of the system, then you have several variety of people interacting: design, development, manufacturing, operations, maintenance, dismantling. These people don't generally interact among each other by anticipation. Sometimes they interact by accident, and then it could be difficult. So in fact, we need to anticipate all this. Human-centered design, when we say human-centered design, the humans are these, deal with these varieties of people, actors. Third, emergent properties and behavior, not included in the components. I already said that. So we need to, find out as early as possible these emergent properties. And this is why modeling and simulation and human-in-the-loop simulation are so important. Complex adaptive mechanisms and behavior. This is the question of adaptability. And then also non-linearities. Sometimes, because the complex system is a system of systems involving systems that interact among each other, then you have non-linearities there. And then it's very difficult to anticipate what could be happening in very sophisticated situations. So again, modeling and simulation is really important. So for the method and tools, the key point is integration. And in industry today, until very recently, integration was done too late, almost in the end. People were designing the parts of a system, systems of a system of systems, if you like, and it's recursive definition of system. But the integration should be thought as early as possible and incrementally, in an agile manner, if you want, developed until the system is operational. So design thinking and creativity and ideation is the first thing. The second is task analysis and scenario-based design. Conceptual modeling. I will introduce the method PRODEC in a few minutes. Rapid prototyping, human-in-the-loop simulation, evaluation methods and tools, agile development, and organizational design and management. Anytime you design a complex system, the way it's organized, not as a product only, but organized as a process of making it, is very important. In other words, if I take the music, a musical analogy, if you want to design a symphony, I mean, you need composers, a composer that will design, scores for the musicians that are coordinated among each other. So in fact, this is about the organization. Okay, so integration is the key issue, and from the early stages of design. So I like to introduce this schema here. You have this, life cycle of a system, from design to manufacturing to certification, operations and support, and dismantling in the end, that we sometimes forget. Then today, using a technology-centered engineering approach, then because if you design an aircraft, for instance, you are connected with suppliers, and the resource commitments are made most of the time too early, because you need to work together, and they have on-the-shelf products that you need to use and probably modify, but okay. So the consequence is the design flexibility drops immediately, in fact. And then you learn about the system by using it, by making it in the beginning and using it. So in fact, this curve here, we would like to put it back to the left. And then human-centered design using modeling and simulation enables to do that. If you have a good model, and today we have very good models. I mean, we have models of, the architectures, structures, functions, aerodynamics, whatever. We have very, very good model, more and more. It's not totally tangible, but it's tangible enough to be considered. And then, so in fact, you can run human-in-the-loop simulation and discover, system knowledge, the more knowledge on the system. And then the design flexibility is not dropping immediately, because you deal with software in the beginning more than hardware, and then you can keep, the design flexibility at the high level later than before. So in fact, and in fact, also the concavity of the curve is opposite. And then the resource commitments follows exactly the opposite of the resource commitments of the past, because you don't need to commit immediately. You can wait that you understand better the green curve. So in fact, all this has to be done during the whole life cycle. Here I show modeling and simulation in the beginning of the life cycle. But in fact, we are working right now on the maintenance of helicopter engines maintenance, where we develop the so-called digital twin to better understand failures and incidents. Then, this curve here could be expanded. We can expand the digital, the modeling and simulation, and call it a digital twin. It's actually a digital image of the real system, whether it's an engine or it's a air traffic control tower or whatever. So and then you expand that during the whole life cycle, and this is very interesting because you can test the what if, you know. Then it's also vivid documentation of the system that you are developing and using. You can incrementally reintegrate experience feedback. You know, this is and then we are working right now on these digital twins that are modifiable, either using machine learning, but the concept of machine learning here should be flexible enough to take into account what we call human supported machine learning. And then this is also an organizational memory of the system. And then, in addition to that, the more you go, the more the digital twin becomes close to the reality, if you want, I mean, tangible. The more you can consider that as a virtual assistant. And then you start to deal with this collaboration with a digital agent, a virtual agent. So I will come back on that. I mean, I will take examples during my fourth lecture on an air combat system that we have developed and that deals with this issue of trust and collaboration. So one thing I want to introduce at this point is this schema here. You know, in our field, aviation, aeronautics, but also in space, I mean, in nuclear energy, in oil and gas is the same. We use procedures, operations procedures, that one way or another, they automate people. You know, the people need to apply the procedures, not to think too much, to go ahead and use the procedures. Then you automate human functions. And then you have, beside that, you have automation that automate machines and produce the automation of system functions. All this is defined in very specific context in what we call expected situations. And when we have enough knowledge on what is going on in aviation, for instance, we have a lot, I mean, very, very sophisticated knowledge on flights, and but still it's rigid, because when you have a new event that you don't know or you don't anticipate, then things becomes difficult, because neither the procedure automation could be used as they can be used in expected situations. Then the system may become rigid and sometimes catastrophic. So now, what do we do with unexpected situations? This is the question. So we have to solve problems. And who can solve problems? People. Then we have this issue of autonomy of people. Are the people inside these complex systems autonomous enough to solve the situation and survive, if I push to the limit? Then what we realize is that most of the time you need to interact. I mean, these people need to interact with other people, and then these other people need to be coordinated. You know, I will come back on that in a few minutes, but the Apollo 13 successful accident, it's called, at NASA, is a good example of that. I mean, the ground people helped the astronauts to recover. Then we are in the field of flexibility there. Then, but flexibility need to deal with competence in problem solving. So in fact, it's flexibility and autonomy and problem solving. Then all this could be summarized in a concept of allocation of human and machine functions. Then if we consider only the rigid part, we may end up with very terrible accidents. Then we need to deal with this flexibility. And this is why I have a chair at Central Supélec and SCIA called FlexTech. And I will tell you what a FlexTech is about. You know, you remember this concept of high-tech systems? Then FlexTech is this kind of systems that help people to recover and provide some flexibility in the recovery. Then the slogan here is going from rigid automation to flexible autonomy. Autonomy being not only system, but mostly people. And then this autonomy implies that we deal with multi-agent systems. We cannot solve the problem with the conventional approach, the traditional approach of single agent systems, a human in front of a machine only. We need to consider a system of systems. So HSI is a combination of human-centered design and systems engineering. And I would put system of systems engineering. So the approach, you know, the traditional approach is technology-centered, producing automation, procedure following, and leads to rigidity, especially in unexpected situations, and people adapt to systems necessarily. Now, if we go into this digital engineering where we are today, where we can simulate and we produce a lot of systems that are software intensive, then we can develop what we call now human systems integration. Human system integration, and being what I said in the previous slide, a combination of human-centered design and systems engineering. Then we can go to autonomy, being based on problem stating and solving. I put stating here because, you know, solving a problem that is not very well stated is not good. So we need to learn how to state a problem. And then disciplines that needs to be taught and learned is human factors and human in the loop simulation and other things. And data science and artificial intelligence could help here. Data is very good, is very important. And then the idea is to lead not to rigidity, but to flexibility, using other approaches like creativity, complexity analysis, agility, tangibility, and maturity. And I will show you that maturity is not only a matter of technology readiness levels, it's also a matter of other things. And then system and people adapt or co-adapt. This is what HSI is about. Then we want to go towards more autonomy and flexibility. So when we talk about problem solving, it's not only in operations, but also in engineering design. So what is a FlexTech? I wrote a book recently, that was last year, Design for Flexibility. And then I would like to provide some examples using this top model, technology, organization, people. And people, you don't design people, but you design competence. So let's take this example, very simple example. You're typing a text. And then, you know, you're very lucky if you don't make typos. I make typos. But if you don't have the undo function, then it's pretty rigid. Undo is a FlexTech, in fact. This is the simplest example I can give. Undo is not a procedure, is a FlexTech. You realize that you make the typo and then you correct it, and you have the device, I mean, you have the FlexTech to correct it. So this is related to technology. Now, organization. I talked about this Apollo 13, what we call successful accident. And this was a collaborative problem solving, in fact. You know, I told you, you know, flexibility is related to problem solving, and problem solving is related to flexibility. So here what the flight director did is Gene Kranz at that time. I said to his engineers, okay, now this is coming from the movie. I mean, this is a picture from the movie Apollo 13. If you here are all the ingredients that are in the capsule in space. Then let's make a CO2 remover that the astronauts could use to come back to the Earth safe. Then the people made this system, and then they made a procedure that they sent to the astronauts. The astronaut used the procedure, made this system running, and then they succeeded to come back to the Earth. So this is a FlexTech in the sense of organizational support. We have to anticipate problem solving not only at the individual level, but at the collective level. Third point, at the people who are involved. Creativity and experience are two very antagonistic concepts that need to be put together. I want to take this example of the design of this rover, the lunar rover. I was involved in this since the beginning. I was part of the team that designed this rover in the United States at NASA. And then creativity is very important because we had these post-it sessions and this cartoon drawn by two cartoonists, in fact, that we hired, and we were designing traverses because in the team there were 3 geologists that they were very knowledgeable on the moon. One of them actually worked on the moon. There was Jack Schmidt, and in fact we used this knowledge to design scenarios, scenario-based design, and then the cartoonist helped us to design this. And of course, we had lots of experienced people, engineers, NASA engineers, and computer scientists, and etc. That were involved in the reality, in the tangibility of what we were doing. So, in fact, and then we made, these cartoons, and then a model, CAD CAM, and then we made a movie, like Disney actually, a cartoon, and then we made a simulation, and then we built the actual system, and then we tested it incrementally. What we did is we went from virtual to tangible. This is what my last book is about. So in other words, FlexTech is a matter of technology, organization, and people. Technology, I illustrated that as a problem-solving tool support and the undo functions. Organization, problem-solving team, Apollo 13. And people, problem-solving competence, mixing creativity and experience. And that cannot be done by only one guy. I mean, this is a question of multi-agent perspective. Come back always on integration. Integration, imagine from the beginning of the design, requires a systemic approach, a systemic ontology. Like, for instance, making a symphony requires music theory. So what is it? So the first question we ask is, what is a system? Well, most of the people think that the system is a machine. Well, if you talk with a medical doctor, he will talk about the cardiovascular system or the cerebral system, cognitive system. So in other words, a system is a representation of something that could be either natural or artificial, either human or machines. So in other words, a system can be a human system or a machine system. And then also a human system can include a system, like for instance, the pacemaker in the body of someone. But also a machine can include a human, like in a car or in an aircraft. So in other words, and all this is recursive, and you can have systems of systems. The question is, a system is a representation. I mean, the proposal here is a system is a representation that could be represented by a function and a structure, and that at least one function, but it could have many. And then a function could be physical or cognitive, and the same for the structure. So if you I don't have enough time at this point to describe everything, but I leave that for a later talk. So in fact, in the beginning, a system was considered as isolated, but in fact, today, a system is not considered anymore as isolated, but connected to other systems. This is why we talk about interconnected system of systems, interconnected structure of structure, interconnected function of functions, that we need to superimpose on top of the structure. We call that function allocation. And then when we put the system at work, in activity, then we discover emerging functions and emerging structures. And this is what we have done today in the air combat system. During the last few years, we developed that in this context, using some criteria like shared situation awareness, speed and precision, resilience, and trust and collaboration. So in other words, we went to more detail, saying that a system as a function and a structure that could be decomposed by its role, its context of validity and resources, that could be physical or cognitive, both of them, and then could be human or machines that loop with the definition of the system. So in fact, defining an ontology of a system is making these kind of things. I'm sorry, I speed up because I look at the time, and I may actually, how much time do I have? Hello?
Oh, 10 minutes, Guy.
How much?
10 minutes.
10 minutes. Okay, I finish up. Then, in fact, I want to show you this. So these systems, human or machine systems, may belong to three kinds of models. We call systemic interaction models. Supervision, the various systems don't know each other and they need a supervisor. Mediation, it's like two countries, and the mediator could be diplomats. This is the model of a user interface today, with a desktop. You don't know how the computer works, but through the interface what to say to the system and back. And then cooperation, this is only for people, where each system has an image of a mental model of the environment. So the autonomy is going in this direction, and knowledge is going in this direction. So in fact, sometimes we design systems, at the cooperative level, but most of the time they degrade to the supervision model. So we need to develop that. So integration, from purpose to means. The product method, and I will describe that in very quickly. This is the method that we develop. Product means procedural and declarative. You remember in computer science the procedural programming languages and declarative programming languages. This is coming from cognitive psychology with the procedural memory and declarative memory. So we develop first the scenario-based design, the procedural scenarios, and then we try to deduce the declarative scenarios, which are the actors, if you want, the agents, and then we make incrementally an ontology, and then we incrementally make classes of agents and etc., according to the model I already provided. So we are using this in the oil and gas domain at the moment. One of the big company, very well known, decided to replace the people on drilling platforms on the ocean. It's very dangerous for people, by fleets of robots. And then we started to develop this virtual modeling and simulation, and incrementally tangibilize this using real robots and real simulation. Concluding. So what I would like to emphasize is the awareness of various possible contexts. Scenario-based design is really important. Human-in-the-loop simulation are really important to deal with complex systems and the role of people in these complex systems. And then we need to look for emergent cognitive functions. So I said that already, scenario-based design. And you know, you need to believe me at this point, but we end up with very solid conceptual models doing this. We take often the metaphor of the orchestra model. I talked about that during my presentation. You know, we need to find this music theory, the common framework that could be shared among the various actors, you know, in the field where you work. Composers, there are very few composers today in the industry. They are the people who make the contracts and the coordination between the people. And the conductor is these people who are good at dynamic reallocation of functions. And the musicians, the competence, engagement, and cooperation, that are the main factors. And the audience, I mean, the people are using the system, or the, you know, and they need to be in constant communication and education. What do you say to the people when you design a new system? That's a very, very, very difficult thing. A few takeaways. We live in a digital world. Tangibility is a crucial and contemporary issue. I wrote a book, by the way, on tangibility. Single agent ergonomics is not enough. We need to go to social ergonomics. And we have an article that describes what social ergonomics is about. Was done last year. He won a prize, by the way. Human-machine teaming. What new human roles? You know, when you have a machine that decides some kinds of things and offer you some support, what is the role of people? Here, trust and collaboration are at stake. Rigid automation is what we know today, especially in unexpected situation. Flexible autonomy is what we need to make. How do we deal with the unexpected? This is the topic of the next talk, the next presentation. We used to go from means to purpose, meaning we design the technology first and we say, try to discover the usages afterwards. Today, we should start the opposite, from purpose to means, using human-in-the-loop simulations. Collaboration work requires education, openness, empathy, and enthusiasm. So this is the book, Human Systems Integration from Virtual to Tangible, I was talking about. Another one was, this one is 2020, and this one is 2021. Design for Flexibility. And this is about the work that we have done in my chair, Central Supélec. And then I want to advertise this workshop, HSI 2022, organized by Incosi in Torrance, California. Will be hybrid, you know, in person and also virtual, from the 16th to the 18th of November. It's international, and they will meet industry and academia, and government, and all work. You know, it's a workshop. It's not a conference. We will talk about work in progress, and also we will have other communities collaborating in this workshop: the International Ergonomics Association and the Association for Computing Machinery, meaning the SIGCAI people. Thank you very much.
Thank you for this excellent lecture. I will not even attempt to summarize it. We have a couple of questions and I'd like to go through them. Before that, I would like to appreciate very much the lecture, because it resonates very much with our thinking, and especially when you dwell between the complicated and complex and emergence. That is very much aligned with our 10 system principle white paper. And also I like this dwell on task versus activity, the historic progression from human factor ergonomics to the system engineering through human computer interactions and so on. So I think we have about 10-15 minutes, and I would love to jump into some questions before we wrap up. So I'll take down the way it came. I think to some you already had a slide. For example, this one of Costas Christophorou said, what tools do we have in place for this technical engineering personnel, which in our jargon language, they are called ATSEPs, the air traffic safety electronics personnel, to have a system-wide awareness and also to handle the complex problems as you described coming from the increased automation. So basically what tools we have in place to deal with increased automation.
Well, there is not very many. There are not very many tools and methods on the shelf right now. We are designing and developing a method that we call Product. Unfortunately, I didn't have time to go into details on this, but probably I should take some time next time to develop that. This is based on the fact that we need to articulate the operations with the design, and not the other way around. We need to anticipate early enough. We talk in terms of as is and to be in scenario-based design. Designing a scenario means that you describe a scenario on the existing operations today. We call that as is, and then you project yourself in the future, and this is called the to be, and then you design a new scenario that you play on a virtual prototype, and try to deduce what is good and wrong in the definition of the functions of this prototype, but also the emergent functions that you cannot see in the first place. And then you iterate in an agile manner, the agile development. The question here is this articulation of scenarios, whether they are scenarios, as is and to be, with the criteria that enables you to figure out what should be modified and should be kept. In fact, this is this is the product. So pro is procedural. I mean, the scenario in the original sense, and deck is actually the definition of the various agents, whether they are people or machines. And then we articulate this in a representation that I didn't have enough time to describe. But so we are building a tool right now, helping people to figure out what new technology, organization, and competence you need to develop.
Thank you. The number of questions are growing, so I think some we can defer. For example, there is a request to clarify a bit more on tangibility. I think you can maybe take it in the next lecture.
Right.
There is one common question. I said I don't understand why it was raised while you were presenting this difference between complicated and complex. I didn't stop you at that time, but Munia Masu asked, I didn't understand why complexity is related directly to complexity. I think what you wanted to explain there, it was that, in complex system, you cannot explain that through just the behavior of the components. And if I allow me to elaborate on that one, that's come from our system thinking paper, is that, a complicated system, it's an aircraft engine where we understand it completely. We can put it aside, we'll reassemble it, and we know the functionality. But complex system like, air traffic management, the airplanes are flying different trajectory every day. Stock market, it's a system complex, which we cannot expect all the time to understand the outcome and the behavior. So we need to look at it from system perspective and not from, interaction of the components. Absolutely. I don't know if you want to elaborate on it.
Let me give you an example. Let's imagine you move from a country to another, from a city to another city. Then during the first days, you find the new city, very complex. You don't realize that the bakery is there, or and then after a few months, when you become familiar, then everything becomes much easier. Why? Because you made sense of the nodes and the links between the nodes. So in other words, complexity is, as I said before, is a number of nodes and the number of connections among the nodes that you need to become familiar with. This is why I put familiarity together with complexity. So the way you model the system is really crucial.
That links with very nicely with the next question, which comes from Bianca Gridan. And if I can paraphrase, it said, okay, may read it directly. To what extent can we add complexity to our system before it becomes too much to handle? So where do you stop in designing a system before you think you have reached much more complexity? I mean, you need to bring your crystal ball to answer that question, but
you know, we are in a field where it's not 100% success. But if you are close to 100%, it's better than if you're not. You know, this is the so now more seriously. You know, when you stop, this is the issue of granularity. In fact, this is on the mod. You know, when you model system of systems, what is the granularity of the subsystems, if you want? Okay, where do you stop? And this is true for the, you know, this is true for the engineering design, but during the operations, what should the people, the users, the human operators know about the granularity of the system? In other words, you know, if you build, for instance, a fuel system on an aircraft, you know, for a long time, it was pretty simple. You know, there was a few valves and you know, but now we control that with computers, and there are lots of valves everywhere. You cannot know everything. You know, this is but at what level of granularity you need to know something? You know, that's the question. And this is sorry, but it's empirical. You need to run simulations.
The next question comes from Ben Willems. He said, how do you conduct a human in the loop using a digital twin? I guess simulation using a digital twin. And I think this concern comes because in the most human in the loops activities, we have strong bias from the human operators that are invited to participate in that. So, and even if you are able to do a human in the loop using digital twin, will not be better to lose, you know, digital tools of a human operator and its variations to avoid the bias?
Well, my claim is that human in the loop simulation is requires expertise. You need to build experience on that, expertise, and we may be at the beginning of that, but this is important to you know. And when I talk about tangibility, this is really the question. How far are we from the real thing? This is about tangibility. There are two definitions of tangibility. The first one is physical tangibility. You know, you hold a stick, for instance, you feel force feedback. You know, this is tangible. I hold my pen, you know, I grab my pen. And now there is another definition of tangibility, which is called cognitive tangibility or figurative tangibility. I try to convince you. If you're convinced, which I hope, you tell me, okay, this is tangible. That means that I understand it. I can grab not the pen, but I can grab the concept. I can grab the abstraction, you know. And then this is the articulation of physical and cognitive tangibility that we need to better understand in what we are doing today. And then there are repercussion design, of course.
There are several questions from the same people, so I'll try to select from different people and come back to the questions that we have not answered. I want to come to a question raised by Anders Elstrand. It's a simple but quite direct question. So can you give an example of emergent cognitive function?
You know, I remember. I'm going to take a very simple one that was not so simple during the 80s. You know, during the 80s, we designed, we automated a lot aircraft. You know, aircraft were, you know, we incrementally added automation on aircraft to a point where you know, the aircraft was not flown as before. You know, flying an aircraft was a matter of controlling the various parameters, control. And then after a while, we developed so many systems, we needed to manage the systems, not control, manage. And this jump from control to management is an emergent function. You know, it's like when you get a promotion in a company, you become the boss of a team, and you have to manage people who are doing the same thing as you were doing before. And most of the time you're tempted to micromanage, say, he's not fast enough or what, you know, and then you manage people who are not doing what you have done before, and you have to learn what you know, they how to manage them. So in other words, this is an emerging function management, you know, for the pilots. I am clear?
Yes, I guess. Thank you. Anders is an unusual collaborator, so we'll come back if was not clear, but I think you were clear on that. Let's pick up one from Maria Kujimutsi. He said, could we refer to aware operators in inverted commas in addition to the autonomous people in the system? In what ways do we expect the function of a complex system affect in a negative way the situation awareness of operators, or should the special training be enough to mitigate such negative effects?
So generally speaking, situation awareness has become a real issue because this is related to the cognitive tangibility, in fact. When the people don't understand what is going on, that means that they cannot grab the situation. So they are not aware of the situation, if you want. I mean, we could actually qualify cognitive tangibility as situation awareness in many cases. So in other words, the more you complexify the system, the more you create this non-familiarity. So when you become familiar with the system after a while, because you have you know, mistakes being done and corrected, and you solve problems with the system, then you learn. You become familiar with the system. You know, then well, this is my answer.
Right. Let's keep going with the theme of emergent behavior. So given that emergent behavior can be beneficial or harmful to overall system performance, how we can try to model or predict emergent behaviors to better mitigate their effect. And by the way, thank you from this very inspiring talk from Oscar Burling.
Well, my claim, and I'm taking risk here, is that you cannot predict emergent behavior at the moment. I mean, I don't know how to do that, but you can observe. If you are expert enough in a field, then you can see that there is an emergent behavior. And then this is why it's important to run human-in-the-loop simulation to create activity of people, and this activity make real this emergent behavior and emergent properties. And then once you observe them, you know, it's like I don't know, the concept of affordance. It's almost impossible to predict that, but when you observe, you realize what it is, and then you afterwards you can consider that in the design.
Yeah, I think with that you also partially replied to the second question of Oscar Birling. He said another question about emergence. What are your thoughts about the relation between control and useful emergent behavior? Is there a design dilemma there?
Design is obviously iterative. So because you make iterations, you improve the design, then using this observation of emergent behavior and properties, then you can improve the design. I mean, this is and maturity is coming from there. I mean, it's really, I mean, the more you have experience, the better.
One quick question. We don't know the owner because it's submitted anonymously. Said, what should be done if flexible automation fails along with the strict automation? How can we improve the flexible automation to reduce the failing rate?
Again, I mean, there is no real method procedure if you want. Creativity is important. You need to try. To put people in difficulty sometime, but if you do it in the real world, that could be very dangerous. In simulator, it's better. But there's always this issue of tangibility, of course. I mean, you have to deal with flexibility and tangibility may not work in the same direction. So the thing is, my answer is you have to try, and scenario-based design is important. What are the best scenarios to develop and use to make emerge some emergent behavior?
Right, we have a handful, just maybe a couple of questions, and we complete. I see there are still a large attendance with us, so we'll take them and then we close. From Francesca Matarese said, while human system integration has a great perspective in the offline activities like design, maintenance, training, she said, I think it is a real challenge for regulators and for the safety of operations in online contexts like air traffic control, where human role is crucial. She's seeking what is your opinion, and was the experience of the offshore company successful?
Well, basically, human systems integration is iterative. And today, the good news is that with the digital tools that we have for making models and simulation, you can start very early. Of course, it's not 100% sure that you will find the right emergent behaviors and confirm that the functions that you implemented are good or not. But the digital media could help today to make good simulation, human-in-the-loop simulation, and generate these emergent functions that we are looking for. What is the rest of the question? Sorry, I forgot
No, it was if maybe other industry in the offshore, this HSI has been.
Oh, yeah. I can tell you that the people we're working with an oil and gas company right now, and they are extremely happy to work on these lines, because they discovered things that they didn't anticipate, they didn't think about even, and now they integrate that into the robots and the fleet of robots. I mean, it's not only a question of one robot, it's a fleet of robots. We are talking about 20, 30 robots.
And I will finish maybe with some reflection from a younger colleague, Bianca Gridan. So, well, this lecture probably is giving a concern that we need to reset all our thinking. The existing approaches like system human thinking, if yes, how can the young people learn more about this? This is rather complex and maybe not always covered by university courses. Yeah, okay. You mentioned some of your books. I think these webinars that we are trying to bring forward, it's a drop in an ocean, but leave it to you, Professor. What else? From where they can drink from the source of the new approaches.
So thank you for raising this question that enables me to make some publicity. I'm teaching this in 4 schools right now. One is STI in the Basque Country. The other one is Centrale Supélec in Paris-Saclay University. Another one is in the ISAE Supaéro in Toulouse. And the fourth one this year is the Business School of Paris, in coordination with Centrale Supélec. In fact, this is a Master of Science. So in fact, we are not interacting only with engineering students, but also with business guys. And
Right.
this is a course of 45 hours.
Thank you.
Well, okay, so in fact, we are teaching this.
So the answer to Bianca, a right master, a right at the right university. Right. I know I said I would finish there, but meanwhile, a last question came in because comes from the air navigation providers. I think service provider is good to take it because we are overall Eurocontrol this with ATM and ANS. Said if we consider, is from Hamza Taheri, said if we consider the ANSP a complex system, and I would agree with that, the ANSP is a complex system, then said how the performance indicators could include non-tangible socioeconomic subsystems.
Whew, big question. Well, again, I mean, you cannot do everything, but this is important to work. How can I say that? Design should be participative, and you know, I have this experience working with at NASA with. Of course, we didn't have issue of money, but meaning, I mean, economy or things like this. But still, I mean, but we worked with computer scientists, engineers, geologists, psychologists, sociologists, anthropologists. You know, a bunch of very different disciplines together. And what we are developing in HSI is this participatory design, collaborative engineering kind of thing. And of course, I mean, it's important to include economy and finance in this as well. But we have to be careful, not, you know, in the weight you put in the disciplines, of course. I mean, if from the beginning, the finance guys say, okay, this is not possible. Of course, I mean, everything is blocked. So we have to be careful. So I don't know. I don't want to enter into this technological politics, but this is important to be open.
Right. Thank you, Guy. Thank you for that. And I think one of the takeaways bring diversity in the ANSPs. I think we are quite lacking this diversity of multidisciplinary, you know, disciplines and bringing them in our, you know, anything that we do from design and okay, in operations we need to keep ATC, but the systems that we design for them, we are very much going and buy off the shelf, and then we dwell on the years with the suppliers to make and adjust the system for our operators. But there is very little diversity into that. Some of the NSPs have some human factors departments, some ergonomists are sitting there, but that is very limited. So thank you very much, Guy. I think we can keep you here for hours. Yes, please. One final.
I want to add something. You know, we are teaching now. I have a team around me, about 10 professors and 5 PhD students, and we taught this to 165 students for the last 2 years. So in fact, we are disseminating this. If some, I don't know, NSP or companies are interested, we can give short courses, like 2 or 3 days, if you're interested.
I think there will be an interest, so we take that also as a takeaway, and also we'll make available that information also at the next 2 webinars that are coming, because we have 2 more sessions with you.
Yep.
One is on the 28th of November about under the heading of problem solving and procedures, how people are handling unexpected situations, and that is very important for aviation, for the people in the cockpit, but also for the people in the ground. Right. And of course, we have another one in February next year with a couple of use cases from different industry on how they dealt with the human system integration. And to finalize the publicities, on the 15th of November, we have another session, this time with Michelle Reith, about, it's a follow-up with her on her PhD studies about the automation air traffic control and what came out from her analysis with DFS, the German air traffic controllers. So I'd like to, on behalf of Jörg and myself, thank you, Guy, and thank you all participants, and see you soon on the next webinars.